Machine learning algorithms bog down when you feed them thousands of features. Principal component analysis, or PCA, solves this by analyzing your data and locking onto the axis that captures the maximum spread, called variance. Once found, you project your data points directly onto it, dropping an entire dimension while keeping the relative distances intact. You lose the bulk, but keep the big picture. But there is a trap. If you feed PCA a dataset mixing different units, the algorithm will chase the larger numbers, completely skewing your principal axis. The fix is feature normalization. Passing your data through standard scaler forces a uniform scale, allowing PCA to find the true mathematical axis instead of being tricked by large unit sizes. Failing to normalize guarantees your dimension reduction will be mathematically flawed. Look at these MNIST digits. A single digit is just 28 by 28 pixels, but flattening that gives us 784 individual dimensions. To train efficiently, we must compress those dimensions down to a fraction of their size without destroying the actual shape. This plots the explained variance ratio. It tracks how much information we retain as we add dimensions. Notice the elbow in the curve. By the time we reach 154 dimensions, the curve flattens out, showing we safely retained 95% of the original variance. Instead of calculating this manually, you can tell scikit-learn the percentage of variance you want. Passing 0.95 into n components automatically finds the correct dimensions. Accepting a 5% loss in variance drops the feature count from 784 to 154, shrinking dataset size by 80%. This side-by-side comparison shows the original digits on the left and the compressed digits on the right. If you look closely at the edges, you'll see a slight blurriness due to the 5% variance we dropped. However, the digits remain perfectly readable. Let's test that scikit-learn shortcut. If you wanted to compress a dataset but ensure you retained exactly 90% of the variance, how would you write that PCA initialization? You pass the float value 0.90 to n components. Standard PCA requires the entire dataset to fit into your memory. For massive datasets, the solution is incremental PCA. You divide your data into mini batches and feed them into partial fit. This updates components chunk by chunk, keeping memory under control and preventing crashes. The 3D Swiss roll dataset exposes standard PCA's weakness. It is strictly linear. Linearly projecting a twisted manifold onto a 2D plane destroys its structure. Instead, kernel PCA utilizes the kernel trick to perfectly unroll the complex twisting manifold into cleanly separated 2D data. To execute, normalize features first. Target your variance percentage using a float value. Use incremental PCA for datasets exceeding your RAM. If your data twists, use kernel PCA to unroll it. Strip away background noise and focus on the true